Hello students, good afternoon. I welcome you to this session. Uh, Today we are going to start fluid dynamics. Okay, in the first three lectures of this week we covered fluid statics. Today we are going to start fluid dynamics. Okay, and today we'll be talking about Bernoullis principle. Okay, and yesterday, in an unfortunate event, we lost our connection 10 minutes before the end of the session. And at that time, I was discussing the equilibrium of the floating bodies. Okay, I couldn't complete that. Okay, so I will start with that part only, and then we will move into the discussion of fluid dynamics. Okay, so being said that, let's share our screen here. So here we go. So let's talk about equilibrium of floating bodies. Equilibrium of floating body. Okay. So yesterday I already said that let's say there is some object like this which is floating. Let's say this is water and this is a solid body floating in it. Okay. So when it is floating, we have already realized that it got to be in equilibrium. So by equilibrium, we mean to say it would be in translational equilibrium as well as rotational equilibrium. So in order to establish that, okay, let's try to draw the free body diagram of that body. Okay, so there would be some center of gravity of this body. Let's say it is somewhere here, that is center of gravity. So effectively, its weight would be acting at the center of gravity. Okay, and there would be something called center of buoyancy, which we have discussed yesterday only. So there would be some point which would be the center of mass of the submerged part of this body, and this would be center of buoyancy. Sorry, I have put the weight opposite. So weight would be downward, whereas the buoyancy would be upward over here. So these will be the forces acting on this body. Okay, and under the condition of equilibrium, what we can say that W will be equal to B. The net force must be equal to 0. So that is nothing but net force is equal to 0. So that gives us W is equal to B. And also we must realize, like for the rotational equilibrium, net torque on this body is also going to be equal to 0. That means this B and this W should net torque about these net torque due to these forces got to be equal to 0. So being said that, what we can say, like these 2 points will be lying, okay, on a vertical axis. Okay, so now you can see that buoyancy and weight are not producing any net couple over here. So you can say, like if we join B and C by an extended line, that extended line is going to be along the vertical in this equilibrium condition. And we can also say, like this is some axis of symmetry for this body. Okay, so this is the condition for equilibrium. So now we wish to investigate, okay, if we disturb this body slightly, okay, whether it is going to come back to its it will, like some restoring force will act on it or not, so that it will be brought, it can be brought back to its this original position. Okay, so we want to investigate its stability of this equilibrium. So different cases we can consider. Okay, so let's say this is the body here. Okay, and the first condition I will be taking, this is the axis of symmetry, and this is the center of gravity, and this is the center of buoyancy. Buoyancy is acting upward, weight is acting downward. So the first situation is, if we displace it slightly, in horizontal direction. So if we displace it slightly in horizontal direction, that means the relative position of C and B, nothing is going to change. Okay, neither the volume, the fraction of the volume that is submerged in the liquid is going to change. So there is no there there will be no change in the status of force here. Okay, so equilibrium, although we are disturbing the position horizontally, but the status of force will not be changing. So no restoring force or no change in force will be acting on that. Like you can say df by dr will be equal to 0. df by dr here, or dx, whatever you want to say, that will be equal to 0. So that basically gives neutral equilibrium. So that thing is understood, that if it is displaced slightly in horizontal direction, there would be no change in force. So the equilibrium got to be neutral equilibrium. And now you see, like if we displace this body vertically, okay, for example, if we are displacing it vertically downward, so if we displace it vertically downward, you must realize its weight is not going to change, but since the submerged part of the body is going to increase, the buoyancy will increase as well, because the volume of displaced liquid will increase, so weight of the displaced liquid will increase as well. So buoyancy will increase, weight will remain same. So in that case, when buoyancy exceeds the weight, okay, the net force on it is going to be in vertically upward direction. So you can see that df by dy is basically a negative quantity. So this suggests that that is a stable, you can say that is stable equilibrium, because the force that is acting over here, the change in force, is in the direction opposite to the displacement. Otherwise, other way you can also see, like for example, if this body is displaced vertically upward dy, okay, so now the volume of the submerged part will decrease, so the buoyancy will decrease. Okay, so in that case, weight will be exceeding the buoyancy, so the net force on this body will be in vertically downward direction. So this is the direction of df, you can say. So clearly you can see that df by dy is negative only, so that again gives you stable equilibrium position. So we have seen how does this body behave, whether the equilibrium is stable or unstable, if we displace horizontally or vertically. So now let's get into the situation when we will be tilting this body or rotating this body over here. So let's have the diagram. Say, or let's tilt it for instance. It would be looking something like this. And let's say this is floating. So this is something like this. Okay. And let's say the axis of symmetry will still be like this. This would be the position of center of gravity, and this was the original position of center of buoyancy. But you must realize, as this body has been tilted over here, the center of buoyancy will shift towards the right of axis of symmetry, because towards the right, like for example, the more part of this body towards the right is inside the liquid over here, so center of buoyancy is going to shift somewhere, let's say b dash somewhere over here. Okay, so we have changed position of center of buoyancy, and center of gravity is still same. So let's analyze the forces now. We have tilted it in clockwise direction, let's say. So now let's analyze the forces. So its weight is going to act effectively at center of gravity, and its buoyancy b is going to act, or simply b dash, say the magnitude will also change, is going to act in vertically upward direction and effectively at point B dash. Okay, so let me introduce one more point over here. So see, if we draw a vertical line passing through point B, it is going to intersect the line of symmetry somewhere. Okay, and this point C, or this point, let's say name it M. This point M is known as meta center. Okay, let me repeat again. What I have done is I have drawn a vertical line passing through B dash. B dash is the shifted position of center of buoyancy, and this vertical line is going to intersect the line of symmetry someplace, let's say here. So this position, this point is known as meta center of this body over here. So if this meta center, now you can see, so looking at this meta center, we have a way to analyze the stability of this body. Okay, so now you see, for example, um, in this diagram, you can clearly see that this B dash will be now producing anti-clockwise torque about an axis passing through C. Or in other words, you can say like B dash and W will be producing an anti-clockwise couple. And that torque will be responsible. See, we have tilted in clockwise direction, and the torque, the change in torque is in anti-clockwise direction. So what you can say that d tau by d theta is basically negative over here. So this gives the condition for stable equilibrium. This is the condition for stable equilibrium. You can clearly see through the diagram. And another way to look at it is, like for example, in terms of meta center, we can say in case of stable equilibrium, meta center will be lying above the center of gravity, you can say. Okay, so whenever this just by geometry, you can see if meta center, the position of meta center is above the center of gravity, then we can safely say that the equilibrium is going to be stable. In terms of torque, restoring torque, we have also analyzed this situation. Okay, so that is one idea. Let me draw one another diagram where we will be looking at unstable equilibrium. Okay, and we will be analyzing that situation in terms of meta center only. So let's say this is line of symmetry, and let's say that is floating. Okay, and this was nothing but center of gravity. This was the original position of center of buoyancy, but let's say it has slightly shifted. Let's say uh, B dash is here. Okay, so now you see, when I will be drawing the forces, the weight would be in vertically downward direction and the buoyancy would be in vertically upward direction. And now if we draw a line, vertical line passing through B dash, it is going, in this diagram we have put it such a way that it is intersecting the axis of symmetry here. Okay, so this is now the location of meta center. So in this situation, you can see meta center is lying below the center of gravity over here. So looking at the diagram over here also, you can see, since we have rotated it clockwise, d theta is clockwise, and now you see like this buoyancy is going to produce a clockwise torque as well about the center of mass, or in other words, you can also say that B dash and W are forming a clockwise couple. So in that case, d tau is also in clockwise direction. So clearly you can see that d tau by d theta is a positive quantity. So that clearly indicates that it is an unstable equilibrium. And another way of looking at it, by looking at the geometry, we can clearly say that in case of unstable equilibrium, the meta center will be lying below the center of gravity. I hope I am understood over here. And the another situation, you can also have the condition for neutral equilibrium as well. Let's look at the geometry of that also. So let's say this is the body, and this is the line of symmetry, and this is floating over here, and this is center of gravity, and center of buoyancy shifted at this position. So what we can say is, if we draw a line passing through B dash, okay, in this situation I have drawn it such that like it is intersecting the line of symmetry at the location of center of gravity here also. So here when you draw the forces, so you can see the weight is in downward direction and the buoyancy is in upward direction. So here in this situation, d theta is in clockwise direction, but you can see there is no net torque. D tau is equal to 0. So clearly you can say d tau by d theta is equal to 0. So this gives us neutral equilibrium. This gives us neutral equilibrium over here, if this is the situation. And in terms of meta center, you can say that C and M coincides with each other. Okay, so this is how, looking geometrically, just by looking at the position of meta center, we will be able to predict whether the equilibrium is stable or unstable or neutral in case of when the body is slightly tilted or slightly rotated. So here we have discussed the equilibrium of floating body. Now it's time for us to move into the discussion of hydrodynamics or fluid dynamics over here. So let's start. Fluid dynamics. In comparison to the study of fluid statics, fluid dynamics is a little bit complicated. It can be a little bit complicated, but with some realistic assumption, we will be really simplifying it. Okay, so let's first talk about those realistic assumptions. Okay, so firstly, we will be restricting our discussion of fluid dynamics for steady flow only. Okay, so we will be discussing what exactly is a steady flow first of all. So for steady flow, a flow is said to be steady. You can write a flow is said to be steady if flow conditions, flow conditions means like pressure and velocity at a point, flow conditions at a point or at any point, you can say, doesn't changes with time. Okay, so if you take any position in the flow pattern, okay, the pressure and velocity at a point is not going to change with respect to time. And another thing you need to understand about the steady flow, okay, you can say a line of flow in that case will be known as streamline. Okay, let me illustrate it by drawing a diagram here. So let's say this is some pipe. Okay, and here, in order to illustrate the pattern of flow, we are going to draw some streamlines. Okay, so now you see these are streamlines. Okay, so if we choose any point on the streamline, let's say this point we have chosen. Okay, so let's say this point is A. So at point A, at different times, different particles of fluid is going to pass. Like this is a flow line, like the particles are following this line over here during the flow. So all the particles which are going to pass through point A, okay, will be having same pressure and velocity condition even if the time changes, it will not change with respect to time. So pressure and velocity at point A is going to be constant with respect to time, okay, for this steady flow. That is why this flow is named as steady. So, and another thing is, like, all the points, all the particles, you can say, will be following the same path, okay. For example, if a particle has crossed A and there is another point on this streamline, so a particle, if it has crossed A, okay, at some instant, at some another instant, it is going to cross B only. So what we can say, all particle passing through a point follows the same path, and hence we have a unique line of flow passing through a point, you must realize. And these lines here are known as streamline. These lines we have drawn in order to indicate the pattern of flow is known as streamline. So in other words, steady flow is also known as streamline flow. And you might have studied the pattern of electric field lines or gravitational field lines or magnetic field lines. So similarly, you can study the pattern of streamline also. For example, if at any point, if we wish to find out the direction of motion or direction of velocity, what we simply need to do, for example, at A, we wish to find out the direction of velocity of the particle, we just need to draw a tangent at that point, and here the velocity will be along this tangent over here. This would be the direction of velocity. For example, here, if we are to find out the direction of velocity of this particle, so this would be somewhere like this, along the tangent. And you should also realize that two streamlines may never intersect with each other, okay, because if they intersect, let me describe it over here. So this is, let's say, one streamline, and this is, let's say, another streamline, and say they are intersecting at this point. So at this point, if we draw the tangent on this line, this will be along this, and if we draw a tangent on this line, this curve, okay, so this will be along this. So at this point P over here, we are getting two direction of velocities, which cannot be true, because a point will be having only unique direction of motion, so it cannot intersect over here. So two streamlines may never intersect. So this is the pattern of field lines. And one another thing you should notice over here is, see, here in this region, in this part over here, you can see the separation between the streamlines are large, and here in this region you can see the separation between the streamlines are smaller. So this is indicative of the speed of the flow in that region. So what we can say here is, smaller the separation between streamlines, greater will be the speed. Greater will be the speed in that region. Okay. So clearly, just by looking at the pattern of streamlines over here, let's take one point P here and another point Q here. So you must realize this is Vp and this is Vq. So in this region, you in the region of Q, you can clearly see that the field lines are closely spaced, and in the region of P, you can see that the streamlines are widely spaced. So very clearly you can say that Vq is greater than Vp. Speed at Q would be greater than speed at P. So this was about something about streamline. Okay, so the realistic assumptions we were talking about, in order to study the fluid dynamics, we will stick to the discussion of steady flow of an homogeneous, incompressible, and non-viscous fluid. So let me tabulate these assumption. What assumption we would be using over here? So first assumption: the flow must be steady. Flow is steady. That would be one assumption we will be taking. And second assumption we would be taking is homogeneous. The fluid must be homogeneous and incompressible also, you must say. And there must be no energy losses during the flow. So we wish to have a non-viscous fluid for our analysis. So with these assumptions, so we will be proceeding our discussion. So like in any discussion we are going to put here, okay, these assumptions must be already assumed. Okay. So let's have one simple problem with regard to the streamline flow. Let's look at this problem. Let's say we have a streamline flow, and this is how the streamline looks like. Okay. And at this point, let's say the velocity is v. Okay, and the radius of curvature at this point, let's say this is the center of curvature at this point, and let's say this is the radius of curvature. Okay, so let's take one point above this streamline, let's say point number 1, and let's take another point below the streamline, point number 2. We wish to find out, is there any pressure difference of pressure between point 1 and 2? Okay, and if there is, the at which point 1 or 2 the pressure is greater, and what is the pressure difference we intend to find out. So what quantities we are given, that let's say radius of the curvature at this point r is given, and the velocity of the flow at that point on the streamline, that is given to us. And apart from that, like the density of the liquid which is flowing through that streamline, rho, is given to us. So we wish to find out the pressure difference between point 1 and 2. Point 1 and 2 are very near, very near to each other, and that is very near to the streamline as well. Okay, so in order to do that, we just need to do the force balance. So let's take an element of fluid over here. Okay, let's say its cross sectional area is dA, and let's say this thing is r. So its width can be written as dr over here. Okay, so now you see, when we are going to balance the forces on it, so what all forces are acting on it, let's try to figure out. So the liquid from the bottom, like the lower side, would be pushing this in this direction. Let's say the pressure here is P, so the force is going to be P times dA, you must say P times dA. And liquid from the above will be pushing it in this direction, and let's say the pressure here is P plus dP, and that multiplied with dA is going to be force. Okay, and apart from that, so since this is moving along a curved path over here that you can see, so this thing is going to experience a centrifugal force that will be away from center, and that will be equal to dm into v square by r. So now let's balance all these forces. So when we will be balancing these forces, the net force towards the center is nothing but dp into dA, and net force and the force away from the center is equal to dm into v square by r. So what would be dm over here? Dm would be density times the volume of this element. So density is rho, and the volume of this element, you can write it as dA into dr over here. So rho into dA into dr is going to be the mass of this element, and that multiplied with v square by r over here. Okay, that would be the force balance equation, and you can see that this dA gets cancelled, and dP is nothing but rho v square dr by r, you can see. So basically you can say the pressure difference is rho v square dr by r. Let's say dr is the distance between these two positions, small distance you can say. If you want to if you are having some finite distance, you can integrate this equation both sides to get the pressure difference. And clearly it is clear from this discussion that p1 is greater than p2 over here. So this was one question related to streamline flow. And now let's move on to the next discussion, which is equation of continuity. We will be talking about equation of continuity. Okay, equation of continuity, it simply follows from principle of conservation of mass. Okay, let's say for example, let's say we have some piping system which looks like this. Okay, and some liquid is flowing inside it. So let's draw the, you can say, the streamline also. I'm trying to draw the streamline over here. Okay, so this is streamline flow. Okay, and let's take one cross section here. That is, let's say cross sectional area is A1, and let's take another cross section here. The cross sectional area is say A2. Okay, A1 and A2 both are small, so although the diagram indicates that like these areas we have taken large, but A1 and A2 you should take small. So here, let's say the velocity here is V1 and the velocity here is V2. Okay, so these are the velocities at these cross section of the fluid. Okay, so I wish to establish equation of continuity. So before establishing that, let's try to understand what one term over here, which is you can say mass flow rate. Okay, let's have a relationship for this, that is mass flow rate. So mass flow rate in a pipe, so that would be dm by dt, mass flowing per unit time, dm by dt, and dm could very well be written at a cross section that is going to be rho a dx by dt, and dx by dt is nothing but the flow velocity, so you can say that would be equal to rho av. That is something called mass flow rate. And similarly we can have another term which you can say is volumetric flow rate. Okay, so a rate of flow of volume with respect to time, so d capital V by dt you can say. So that is obviously going to be equal to dm by dt, that is mass flow rate upon its density. So that is simply going to be a times v over here. So we have defined mass flow rate and volumetric flow rate. So the equation of continuity simply suggests that in this piping system in steady state, like if there is no longer accumulation inside this pipe, okay, so whatever the liquid is going in, the same liquid will be coming out. Like the mass flow rate inside, the rate of flow of mass which is going inside the system must be equal to dm by dt out. Okay, because this piping system over here between these two cross section, the accumulation of liquid is no longer happening. Okay, and it is homogeneous as well as incompressible. So we can safely say that the mass of the liquid between these two cross section is gonna be conserved. So with whatever is the mass flow rate in, that must be equal to mass flow rate out. So this follows, this is basically equation of continuity, and it simply says that dm by dt in is gonna be equal to dm by dt out. Okay, so in other words, so since we have already had a relationship dm by dt is equal to rho av, we can write it as rho a1 v1 must be equal to rho a2 v2. Okay, and since we are talking about homogeneous incompressible fluid, rho at both these cross sections are same, so the final relationship we have arrived at is a1 v1 is equal to a2 v2. Okay, so this relationship here is known as equation of continuity. Okay, so one another thing here I want to discuss is something called thrust force. Say, let's talk about thrust force exerted by the liquid on the pipe. On the pipe or piping system, whatever you want to say. So see, let's say we have some pipe here. Let's say this is one cross section A1 and flow velocity is V1, and this is another cross section A2 and the flow velocity is V2 over here. So let's say the liquid is going in from this cross section and coming out from this cross section. Okay. So so as you see, like whenever some influx of mass, like whenever the mass of the system is changing, whenever there is a variable mass system, okay, so it experiences a force known as the thrust force. And this expression, you might remember, the expression for thrust force is given by v relative, okay, dm by dt. Okay, where dm by dt is the rate of change of mass of the system. Okay, so here I am going to analyze how the ingoing liquid and outgoing liquid are going to exert force on this piping system. So before that, let's analyze this equation a little bit. So first situation I am going to say, we are going to look at it, is when fluid is entering the pipe. So when fluid is entering the pipe, you can say that dm by dt is going to be positive because the fluid is entering into the system. So system's mass is changing positively with respect to time, or increasing with respect to time, you can say. So if this is the case, looking at this relationship over here, this dm by dt quantity is positive, so you can say the thrust force will be along v relative. So in other words, you can say, like, if this is v relative, okay, this is the relative velocity of the flow, incoming flow with respect to the pipe. So in that case, the force, the thrust force exerted by the liquid is going to be in the same direction as this relative velocity. So let's say this would be f1 over here, and this direction I have already shown. Okay, and the second case you can look at is if fluid is coming out, fluid is exiting, let's say. So obviously dm by dt is gonna be negative over here. So looking at that expression, like v relative multiplied with a negative quantity is equal to the thrust force, that simply suggests that the thrust force will be opposite of V relative. Like in this case over here, when it is exiting, let's say with V relative velocity, V2 relative, you can say that was V1 relative. So the force it is going to exert on this piping system is going to be in opposite direction of V relative. So this is going to be F2. So obviously V relative dm by dt we have written. When we are going to write the magnitude of this thrust force at any cross section, dm by dt, you can write it as rho a V relative. So this term is going to be rho a V relative square. Okay, so please do remember this expression. This is very, very important. Like say for example here, the thrust force will be rho a1 V1 relative square, and the thrust force here is going to be equal to rho A2 V2 relative square. So let's draw the free body diagram of it. This pipe over here, so it is experiencing a thrust force F1 in this direction, horizontally rightward direction. Okay, and it is also experiencing another thrust force exerted by the outgoing liquid, that is F2 in this direction. And let's resolve it into components and say for instance this angle is theta. So effectively what you can see when I am going to redraw this diagram here, okay, so this would be something F1 minus F2 cos theta, and this component is going to be F2 sin theta. So so this is experiencing this much force. So in order to hold this pipe static, okay, so what we must do, we must apply equal and opposite force, holding force you can say. So the component of the external force which we are applying, F external Y and F external X. So F external X is going to be equal to this quantity and F external Y is going to be equal to this quantity. Theta should be given in the question, and F1 and F2 how to calculate we have already discussed. Okay, so let's take one problem here, one simple question, and we will get a better understanding of this situation, that how the liquid is exerting thrust force on this system, and how are its expression gonna look like. Okay, so let's have this problem. Let's say we are having a trolley, okay, of say mass m is equal to 10 kg. This is a trolley which has mass 10 kg, and to this trolley a piping system is attached. Let's say something like this, a piping system is attached, okay, and that is of uniform cross section, and let's say this cross sectional area is 2 into 10 to the power minus 4 meters square. Okay, and you must say like liquid is going like flowing through it continuously, and the velocity with which the liquid is entering this pipe, V naught, is given to us as 10 meter per second. Okay, V naught is given to us as 10 meter per second, and this V naught is with respect to ground. Let's say this is with respect to ground. Okay, and this piping system here is attached, so obviously this liquid will be coming out also, you must realize. Okay, and this trolley is moving on a smooth, free to move along this smooth horizontal surface. Now we wish to find out different things. Like for example, the first thing we wish to find out, like what would be the velocity of cart, what would be the velocity of this cart or trolley at t is equal to 10 second for this instant, for instance. Okay, and the second thing we wish to find out, like what would be the acceleration, or what would be the acceleration of this trolley at say t is equal to 10 second only. And third thing we want to find out here is like at what time v becomes say 2 meter per second, and the fourth, that is the power supplied to the cart when its velocity becomes 5 meter per second. So these all things we wish to find out. So look at the problem here. Okay, so the problem is related to this thrust force, right? So let's proceed with this. And also it is given that initially the cart is at rest. Okay, at t is equal to 0, you can say at t is equal to 0, v is equal to 0. Okay, that is given to us. The initial conditions are given to us. So how are we going to proceed with this problem? So now see, let's first try to find out the force on this. So the force, you must understand, okay, the expression for force is nothing but, I'm only writing the magnitude, that is rho a v relative square. That is rho a v relative square. So in order to do that, okay, we need to first find out v relative. So let's say this is the cart over here at any instant, at any time t, at t is equal to t, this cart is moving with velocity v in this direction. This cart is moving with velocity v in this direction. So if this cart is moving with velocity v, this pipe will also move with velocity v, and water is entering with v naught speed into it. So you can say like v relative here, the relative velocity of the flow with respect to the pipe over here is going to be v naught minus v in this direction. This, so with this velocity with respect to this pipe, it is going to enter, and with the same, since the cross sectional area is uniform, with respect to the pipe, it is going to come out with same relative velocity. So the value of vr here is nothing but v naught minus v. Okay, so what we can write really over here is nothing but rho a and v naught minus v whole square over here. So when you will be substituting the value of rho and a and v naught over here, so what we will be getting here is 0.5 into 10 minus v square. That is what we will be getting. And since this force double, the force would be double over here, because see, this much force is acting in this direction and the same amount of force would be acting in this direction. So whatever is rho a v r square that is exerted at the entry, and the same amount of the force will be exerted at the exit, so double of this, so 2 times, and this will give you this value over here. So this force we have already got. So once we have got the force, we can write the equation of force over here. F is equal to m times dv by dt. F we can equate it with m times acceleration, which is dv by dt, and F we already know, that is 0.4 into 10 minus v square, and m we also know, so that is m is given to us as 10 kg, so 10 into dv by dt. So here we have got a differential equation, you can see, that is dv divided by 10 minus v square. From 0 to v you must integrate left hand side, and dt, and 0 to t, and this coefficient here would be 25 here. Okay, so this is the differential equation we are having. So solving this differential equation, you will be getting v is equal to 10 minus 50 divided by 2t plus 5. So this is the equation. This is the velocity as a function of time. Okay, so we can answer the first question here. The velocity at t is equal to 10 second. Okay, so when we will be substituting t is equal to 10, so we will be getting v is equal to 8 meter per second, right? V is equal to 8 meter per second we will be getting. And acceleration, now you see here this term is nothing but acceleration over here. So just by rearranging this equation dv by dt using this equation right here, we will be able to get the value of v at this instant. You already know. So when you will be substituting 2 over here, the acceleration you will be getting is 0.16 meter per second square. And similarly, in the same relationship, if you substitute v is equal to 2 meter per second for the third part, you are going to get the time over here, and this time is going to be 5 by 8. And the calculation of power is also easy. Like, see, power would be nothing but m times v dv by dt. F dot v we are applying, so m v dv by dt. So v we know, okay, that is 5 meter per second, and dv by dt is nothing but acceleration. So substituting the value of v in this equation, you will get the acceleration over here, and substituting all those values, you will be getting 50 watt as answer to this. So please try to do all these calculation by your own, and all the relevant equations I have tried to discuss over here. So this was one question in which we took the example of thrust force exerted by the liquid on the piping system. So now it's time for us to move on to the Bernoullis equation or Bernoullis principle. Bernoullis principle. Okay, so Bernoullis principle is nothing but a form of work energy theorem applied over a segment of liquid flowing in pipe. So let's take a piping system. Let's say this is the piping system. Okay, so let's take a one cross section area A1 over here, and another cross sectional area A2 over here. And let's take other conditions. Let's say the flow velocity at the cross section A1 is V1, and the flow velocity at the cross section A2 is V2, and this is streamline flow. And other assumptions are also valid over here, like flow is going to be incompressible, homogeneous, and non-viscous, you must say. And apart from that, let's say this is in vertical plane. So let's say this is at height h is equal to h1, and this cross section is at height h is equal to h2. So liquid is flowing in that. And apart from that, let's also say put the pressure condition. So let's say pressure here is P2, and the pressure here is, sorry, here the pressure is P1, and here the pressure is P2. Okay, so these are the flow conditions we have established over here, described over here. The cross-sectional area at a point, and the pressure and the height also. So these are basically flow conditions. Okay, and this is flowing over here. So what will be happening at an instant, at after time dt, you can say this cross section will move by a little. Okay, since this is the flow is happening, this cross section of liquid particles or liquid molecules will move ahead by some distance, let's say dx1. And dx1 is basically, it is moving with v1 velocity, so v1 times dt you can write. And this cross section in the same time duration, this would be moving with some dx2, and that is going to be equal to v2 times dt. Okay, so whatever the liquid was enclosed between these two cross sections are now enclosed between these two cross section, which has been indicated by the blue marks. Okay, so so the conditions have changed over here. So like can we apply the work energy theorem on that segment of liquid? So work energy theorem we want to apply over this segment of liquid, and work energy theorem is basically work done is equal to change in kinetic energy plus change in potential energy, you can say. So here, the work done by some external agent, you can say work will be done by the pressure, force exerted due to the pressure. So liquid at this side will be exerting compressive force on this segment of the liquid in this direction, and this force is going to be P1 times A1. This is going to be the force. Okay, and this force here at this segment is going to be equal to P2 times A2. Notice the direction. The force due to pressure is compressing in nature. So the liquid from the left side is exerting force in rightward direction, and liquid from the right side is exerting force in leftward direction, you can see. So what will be work done by these two forces? So work done by this force, that would be force dot displacement when you will be doing. So that will be work done by P1 A1 would be P1 A1 dot displacement will be simply V1 into dt. And now you must realize work done by this force over here got to be negative, because the force is in leftward direction and displacement here is in rightward direction. So this got to be equal to minus P2 A2 V2 times dt, you can say. So that is the left hand side of work energy theorem, and that will be equal to change in kinetic energy. So change in kinetic energy, so you can say effectively, so this segment effectively has moved over here. So the change, like the in between, there is no change. So whatever change you have to calculate will be for these two small elements over here. So I must write that the change in kinetic energy would be half times mass times v2 square minus v1 square. So that's got to be half, and the mass of this segment. So what would be the mass of this segment over here? So that is going to be density times volume. So density is rho, and volume is going to be a1 dx. So that is a1, and dx1 is nothing but v1 dt. Okay, so this is volume and this is density, so this collectively is mass. So half times mass into, and you must realize also the mass of this segment over here and this segment over here are same, because rho a1 v1 dt would be the mass of this, and rho a2 v2 dt would be the mass of this segment over here. And from the equation of continuity we already know that a1 v1 is equal to a2 v2. So whatever mass has entered through the cross section A1, the same mass flow rate is going to be from A2 as well. So that is basically dm is going to be constant. So the change in kinetic energy would be v2 square minus v1 square. This is delta k. And similarly, delta u we can also write. So this has moved from height h is equal to h1 to h is equal to h2, you can say. So the potential energy is increasing over here. So mass we will be write as rho a1 v1 dt. So m and g into change in height. So that is going to be h2 minus h1 over here. And throughout, since a1 v1 is equal to a2 v2, so this term throughout is gonna get cancelled. Okay, and when you will be rearranging this equation, you will be getting p1 plus rho g h1 plus half rho v1 square will be equal to p2 plus rho g h2 plus half rho v2 square over here. In other words, you can say, in other words, you can say that would be like P plus rho GH plus half rho V square for a streamlined flow that is going to be a constant. Okay, so that is the idea. There is one way of looking at this term, you can see. Like for example, this term you are very well aware of. This is nothing but kinetic energy per unit volume, right? This is nothing but the kinetic energy per unit volume, and this term can be termed as potential energy per unit volume. So this term here we will be terming it as something called pressure energy per unit volume. Okay, so in other words, you can say this work energy theorem is also principle of conservation of energy if we treat the pressure energy. Okay, so that is the pressure, the sum of pressure energy plus plus potential energy and kinetic energy per unit volume is going to be constant with respect to time and position over here. So now you can see, like if in a flow any of these term is like let's say two terms are increasing, so third term is going to decrease and vice versa also. So this is one insight into looking into this Bernoullis theorem or Bernoullis principle. So we have already completed today's time. So in tomorrow's class we will be discussing more about application of Bernoullis principle. So here let's end this class. Okay, and thank you very much for joining us.